All right. Well, it's Friday of week 10, so this is our last class. This is probably your last class of the year. I don't think anybody has class after this, right? But anyway, it's been fun for me. I hope you've enjoyed the course. I think so. Today I'm planning on kind of covering what's going to be on the final exam, so you guys have an idea of how you should study and prepare. And then after that, I'll answer any questions, and then I don't know, we'll maybe cover a fun topic. Who knows? So we'll let's talk about this final exam. Yes.
Is this recorded then?
Yeah, it's being recorded. Okay. But if you want to take notes, you can take notes. There's no rule. All right. So maybe I'll start by saying the final exam is nothing like the midterm exam. Okay. So the midterm exam was very syntax focused, very very much focused on that. Final exam is nothing like that. Okay. Going to cover pretty much everything after the midterm, and so it will cover numeric methods, and randomization tests and Bootstrap. Okay, so that's what it will cover. All right, and I'll just say no floating point arithmetic. So and no ggplot. So those are not on the exam. Okay, all right, numeric methods. Let's talk about this. We covered a few methods. So we've got root finding ones. So for root finding, we have, what do we have? We have fixed point. And we have Newton-Raphson. And we have secant and bisection. And then we have optimization algorithms. So we covered Newton-Raphson, but really it's just any root finding method applied to what? If we want to do optimization, we just do a root finding method and we do it not to the function but to the derivative, yeah? Okay, and then we have a golden section and coordinate descent. So those are kind of the numeric methods. Let me just, sorry, let me write this. Okay, and the way I'll test you on these numeric methods, you'll need to bring a calculator and a ruler. What? Okay. So what I'll do is I'll give you a function, and I'll graph the function for you, and then I will tell you to, I'll give you a function and either an initial point or initial points if your method requires multiple initial points, And then I will just say, like, do 2 iterations of the algorithm by hand. Yeah. So for numeric methods, you know, I will provide a function and graph of the function with and initial point or points, and I will instruct you probably to do 2 iterations, you know. Okay, and to graph. To graph them. Okay, so that's just, I think it's not too bad. Like, so for example, I can say f of x is going to be x squared minus 5 or something like that. Okay, this is like a super simple example, but just to give you an idea, and I'll say x0 will be 8, right? And I'll say, so here is so you've got something like this, right? And maybe I'll say do 2 iterations of Newton-Raphson. Okay, so how does Newton-Raphson work? Well, we're going to start, let's say, at 8. Okay, and this would be that's at 59. And then Newton-Raphson works by drawing a tangent line to the thing. And this will be our next iteration. So x1 is going to be x0 minus this run. So if we do rise over run is equal to our slope, f prime of x, then we can say run is equal to the rise divided by the slope. So it's going to be f of x0 minus divided by f prime of x0. So this becomes, for our algorithm, we have 8 minus, I plug in 8 into here and I get 64 minus 5, 59, divided by, and then f prime of x would be 2x. So if you've forgotten how to take a derivative, maybe it's useful to review taking derivatives. Like last year someone said, what's the derivative of sine of x? Come on. Breaking my heart here, okay? It's cosine of x, okay? So you need to know that, all right? So it's not going to be too crazy. You don't have to worry about like chain rule and I don't know, whatever, all this. I don't know. Maybe some basic things. Okay. All right. And then so anyway, we got 2x, and so we got 8 minus 59 over 16. So this is going to be 8 minus 3 and 11 sixteenths. 5 sixteenths is 3, 1, 2, 5. I think this is going to be 4.3125. Is that right? I don't know. Maybe. Okay. So this is 6875, I think. So we have so you have that. That's going to be x1, and then you do the same thing for x2 is going to be, you know, x1 minus f of x1 divided by f prime of x1. So obviously you'll need your calculator and all this. And then this is what you do. You just graph it, and you'd say this is 4.3125, and then you'd get your next iteration, which, you know, you go up to the thing and you draw something like that. Okay, does that make sense? Is that okay? So that was for Newton-Raphson for root finding, but you should be familiar with all the root finding methods and the optimization methods. Okay. Right, like, and coordinate descent requires you to work in multiple dimensions. So because you're doing it on paper, it can only do it in 2 dimensions. So don't worry about that. But yeah, I mean, so you might have to do coordinate descent in 2 dimensions, and so just be familiar with yourself with these things. And so, you know, if you want to practice, just write up some kind of function and say this is going to be my starting point, or starting points, and see if you can work through it, right? So which methods require multiple starting points? Secant method requires 2 starting points, and then bisection method requires 2 starting points, right? So you need a right bound and a left bound, and then you keep cutting it in half. Okay. Are there any questions? It's okay. Okay, so that's numeric methods, and then we'll have a randomization test. Okay. So I'll provide some, you know, I will write some kind of scenario. And you will write our code by hand to conduct an appropriate randomization test. And, you know, it's probably no more than 10 lines of code or something like that. It's not going to be too complicated. You just need to set up a way for, you know, shuffling your data, sorting them into the appropriate groups, calculating the summary statistic of those things. And then what you want is, you know, one of the lines needs to calculate an approximate p-value. So you'll need one line to kind of set up your baseline observed difference or whatever it might be. You'll have code, a loop, to do the randomization part, to generate a whole bunch of randomized differences. And then you'll need a line to compare your randomized differences to the observed difference to get a approximate p-value, right? Okay. Any questions on this? I mean, if you write more than 10 lines of code, that's fine, but it's probably not going to be necessary. So I know it feels intimidating, the idea of writing our code by hand, but again, it's only a few lines, and while I expect it to be correct, if you're like missing one curly brace or something, that's probably not going to be an issue, okay? But, you know, obviously you need to, it needs to be correct and valid looking, okay? So randomization test, all right. And then you'll also, I'll give you probably a Bootstrap hypothesis test. Okay, and this will be non-parametric. Okay, so you don't have to study either the parametric bootstrap or a bootstrap meta study. Okay, bootstrap hypothesis test, we'll have that. You should be ready to do the bootstrap, quote, manually with sample, sample x replace equals true, or with the function boot, right? So, when you do the function boot, you have to write your statistic function and things like that. So, be ready for either instance. I might have one or I might have the other. And again, this is the task I give you will be able to be accomplished in 10 lines of code or less. I'll make sure that that what I'm giving you is not super crazy complicated. Just make sure that my answer I can do in about 10 lines of code or less, and that's fine. Okay, so this is bootstrap hypothesis test, and again also have a line to calculate the p-value. And the bootstrap and the randomization test are very similar, except bootstrap you sample with replacement, and randomization test you just shuffle the values. And for bootstrap, you use it when the data is obtained via random sample. Randomization test you do when you've used random assignment in the collection of data. Okay, so you got a bootstrap hypothesis test, randomization test. Okay, and then last thing, I'll have a few short answer questions. Covering kind of conceptual topics related to numeric methods, bootstrap, or randomization. Yes?
For that section, the parts that you already said, like, you don't need to study, is that included or not included? So, like, with the parametric bootstrap, would that be included in this section?
I would say parametric bootstrap might make an appearance in this section, maybe. Okay. But I won't put floating point arithmetic here. And I won't do a bootstrap meta study, okay? Maybe bootstrap parametric. So, it'll be something like, so I think this is the example I gave to the other class. It'll be like, only one root finding method is guaranteed to give a root, under certain conditions. Okay, okay, so what is the method and what are the conditions? So only one of the root finding methods is guaranteed to work. All right, well, and what's that? All right, well, you can study. All right, so the method is the bisection method. So that's the only one that's guaranteed to work. All right, and it will work. What are the conditions where it is guaranteed to work? Just the function needs to be continuous. Okay, it doesn't even have to be smooth. It just needs to be continuous on the interval, and the signs of the function at the endpoints of the interval, signs need to be opposite at interval ends. Okay, so as long as one side is positive and one side is negative, and it's a continuous function in there, okay, then well, math guarantees that there exists a root, and the bisection method will find that root. Okay. Okay, and that's a conceptual question. So I won't ask this question, but it'll be related. Questions related to the numeric methods, Bootstrap, or randomization tests, right? Okay. Are there any questions? Yes?
Compared to the midterm, what do you think like the level?
I don't know. Level of difficulty is a subjective thing, right?
You said you thought the midterm was hard. So
Oh, okay. All right. I don't think this is as hard then. All right. But I don't want to say that because I don't want you to feel bad if you look at the final and it was like super hard and now you feel bad about what you learned in the class. Don't worry about it, okay? Just study what I've written up here. Do your best. That's all I can ask, all right? Yes?
What will be the expected length of the system?
It's like 5 or 6 pages, I don't know. But it's like each thing, like the randomization test will be 1 page and the Bootstrap thing will be 1 page and each of these. So you're given 3 hours. I'll be here for all 3 hours, okay? I don't expect it to take 3 hours. Probably, I imagine most will be done in an hour and a half. That would be my guess. But again, I don't want you to feel bad if you're here at 2 hours and 50 minutes and everybody else has left. It's okay. Like, I'm here. You're not inconveniencing me. So it's fine, all right? So don't, it's not a race, right? You don't get any extra points for finishing early. So just take your time and get your answers right and do your best. I don't know. Okay. Anything else? Is that okay? All right. Well, with our leftover time, like I know you don't want to learn anything new, but I thought I would just cover like a kind of a fun topic that's like sort of related to computational statistics and whatnot, and we'll just cover that. On Wednesday, I recorded a video and I posted it, and I don't know if you guys watched it. YouTube says 21 people watched it, but I think 3 of those views were me. So so most of you have not watched it, and that's okay. The Wednesday video, I'm like embarrassed, but I just talk about the statistics department and basically like if you are a stats major, there's like 9 core classes that you have to take, the 100 series, the 101, and the 102 series. And I try to provide kind of a context in which these classes exist so that because when I was an undergrad student, I was somewhere, I didn't study statistics, I studied engineering, but nobody really gave me like this is why you're taking these courses. They're just kind of like, oh, this is the list of classes I have to take, so I'm going to just take them. And it was fine. And then like later on, I kind of pieced them together. But I just thought I would provide a little bit of a framework for like why these classes exist, why we're having you take them, and how they fit in together in this kind of this bigger idea of data science or something like that. And so anyway, it's not essential, but it might be of interest. Let me know what you think. Okay, well, with our time left over, I thought I would cover this topic of kernel density estimation. I don't know if you've heard of this. And the idea is you gather data and you want to represent your data with a nice curve. Okay, so when you think of the normal distribution, you have this nice little smooth curve that looks like a hill. You have the exponential distribution. You've got this curve that, I don't know what it looks like. It looks like some curve, and and you got all these different things, and we represent theoretic distributions with these nice smooth curves. But then when we ask, represent some data, we draw things. Oh, okay, well, this is, we'll draw things with like a histogram. So I would say histogram of X. So here I did 100 values from the normal distribution. And this is our histogram here, and we can modify this, and I can say breaks equals 20 and get like more choppy, or I can reduce the number of breaks. And this is, these are just kind of what our histogram looks like. And then we might look at this thing and we might try to draw out a nice smooth curve. But R actually has a kernel density estimation function, and you just type in density of X, and it produces this thing. But the real power of this is you say plot this thing, and it plots kind of like a nice smoothed out version of kind of this histogram here. And if I were to take just a different sample of normal data, and I say make a histogram of X, this is what we get here, and then we can say make a nice density curve of this, and it just kind of smooths the thing out, right? And let me just do a histogram of X where X limits are equal to -2 to 4 or something. So this is kind of the thing, and then when we turn it into a density curve, we get something that looks kind of like that. And so, how do we get this curve? What does this? We can kind of eyeball it, right? Like if I gave you this histogram and I gave you a pen, you can kind of eyeball a smooth curve. But how does the computer come up with something that looks like this? All right, and so I just thought I would talk a little bit of how this thing works, and then therefore when you look at future papers and they include a density curve of the data, it's not going to be a complete mystery as to where the thing came from. Okay, so that's all. It's so we'll start off with kind of just histograms. And let's say our data, we just have the most simple data. We got a data point at 1 and 2. right? And we can think of, what should our histogram look like? And these are all like legit ways of representing our data. I could have histograms where the breaks are 0, 5, and 10, and my histogram would look like this, right? Or I could have a histogram that looks like this, okay? Or I can also have a histogram that will be 1, 1.0, 1.2, 4, 6, 8. And these are all valid representations of our data, just depending on how wide we make our bins for the histogram, right? And effectively, when we're making a histogram, we can just say we are just dropping, like we're just placing bricks, right? Effectively, we are just placing bricks on the number line. And that's effectively how we make histograms. We say, where's our data point? We're going to put a brick on the number line at that data point. Okay. With kernel density estimation, if we kind of adopt this idea of the way we're constructing histograms is just by putting bricks at data point locations, we can think of kernel density estimation as something similar, except we're not putting bricks, we're going to be putting little like soft wire curves or like just imagine this soft wire mesh curve or something, and we're going to just drop that rather than a brick. Okay, so with a histogram, we put a brick at 1 and 2, and in this place we're putting them at the same location, and here they're kind of next to each other, and here they're separated out. With kernel density estimation, we're going to place a soft wire curve, okay, at each data point location. So again, we will say x is just the values 1 and 2. And you can imagine in the beginning, I will just drop, just imagine here's a rectangular wire, and we're going to just drop this down centered at 1 and 2. That's fine. Okay. And then my thing would just imagine this thing dropping down, and then this is kind of what it looks like. All right, here is, but we could make the wires that we drop down like wider, okay? So here I'm going to drop a wire centered at 1, and I'm going to drop another wire centered at 2. Something like that. And this one's not quite centered, but so these are gonna come falling down. And when they fall and land on top of each other, we're going to get something that looks like this. Does that kind of make sense? So here, I've just imagined this soft wire thing, and here's another soft wire thing, and they fall, but where they stack up, they form like a bump there. Does that kind of make sense what's going on? Okay, so that's what we have, and then depending on how, like, if we have 1 and 2, I could drop even like really wide wires, something like this, and then when we get the result, we get something like this after everything falls and stacks on top of each other. is visually what's happening here okay? Just this kind of this wires falling down and they just stack on top of each other and we get this loose funny thing, okay? And so let me just kind of show you what this looks like. Okay, so X is just going to be the data points 1 and 2. And what I'm going to do is I'm going to plot density of X. The kernel will be a rectangular one, because that's what I've been drawing, rectangular. And then we'll start off with bandwidth equal to just something small. So this is what we have here. So this is kind of this first illustration where they just, the two wires, they don't overlap, so they just stack, oops, like rectangles there. Okay, as I increase the bandwidth, you can see here they've now overlapped a tiny bit in the middle, and so we get this little spike there. And basically I can just keep increasing the bandwidth as such, okay? Here, let me add X. So our data point is right here at 1 and 2, and here I'm just dropping a really wide bandwidth. Basically, in this last one, we have something like this. Okay, so that's all that we have here. This is just a density thing. And so if we had more data points, right? Let's say X is 1 and 2, and we'll say 2.2, right? So here is 1 and 2, and we'll say 2.2, right? And then let's say I drop, here, I'll just do different colors, okay? So here I'm going to drop one thing here, and then I'll drop a thing there, and then we'll drop one I don't know. Does that work? Okay, so let's try this out. And let's try this. So here, okay, so the first one is we've got basically a stack here and a stack here and a stack here. So the result is going to be this, and this is what we have for the first one as the bandwidths increase over here. Okay, and then as I increase the bandwidth, we'll just see kind of just these slightly strange shapes of emerging. And so this is, I think, the one I have illustrated here, which is where they kind of overlap a little bit like this. Okay, so all we're doing is we're just dropping kind of these. You can imagine one wire mesh here and another wire mesh centered at 2, and then the last one is centered at 2.2, and this one gets dropped right there. So that's what we're getting here. Okay, and generally you would not do a density estimation when you only have 3 data points. Okay, but I think having only 2 or 3 data points is illustrative of what the computer is doing, right? And so generally you'd have 100 data points, and it would be a huge inconvenience or a pain to do it by hand. But to ask the computer to just drop these wire stacks on top of each other and then figure out the resulting shape, it's no problem for the computer. Okay, and so kind of with the rectangular one, we can see what's happening. And but we have many other kernels, okay? Okay, and then probably the default one is the Gaussian kernel, which is just, it looks like a normal distribution, and you would just drop it at each location. So if you have just data points at 1 and 2, you can drop skinny Gaussian curves, right? The bandwidth is how wide you want your wire mesh to be. So you can just drop these, or you can have, at 1 and 2, you can drop one that right there and one right there, and then so you'd get something that looks like this. Or if you make them really wide, at 1 and 2, you have this thing and this thing, then the overall thing would look something like this if you drop these curves here. And so let me just go back and just change x to just be 1 and 2, and then we'll do Gaussian kernels. Okay, so there's small bandwidth, and as we increase the width, and just take a look at just what results is that, you know, this middle part that overlaps gets a little bit bigger until at some point everything just kind of blurs out here. Okay, and keep in mind that the original data points are just at locations 1 and 2. Okay, same thing if I add another data point here. Okay, so this is, it was just 0.05, so I've got dot at 1, 2, and 2.2, and then we'll just slowly increase the bandwidth. And so on and so forth. So you could just imagine kind of a curve located centered at 1, a curve centered at 2, and a curve centered at 2.2, and when they all add together, we get this shape here. Okay, so we're just dropping little wire meshes here. And if you take a look at the help for density, we have several different kernels that we can use. So the default is Gaussian, okay? And then I've shown you rectangular, but we also have Epinechnikov and the triangular and cosine, and I don't know what these other ones, biweight and opt-cosine. They're just different kind of kernels that we can use, all right? So the triangular one, so the Gaussian is the curve. The triangular looks like this. And so if I just show you what this looks like, it's just triangles added on top of each other. Okay, so here's triangles, and as they go, you get some interesting shapes like that. And I think especially, so the triangular one, you get kind of 1, 2, as they overlap, you get kind of these interesting shapes here. Okay. The Epinechnikov, this one is it's basically an upside down parabola. Let me just get rid of this. Okay, so here is two things. Okay, so here I've got a data point at 1 and 2, and I've got these upside down parabolas, and you know what happens as I increase. So let me just increase it just a tiny bit. What's going to happen when they overlap a little bit? You get this kind of this funny. I don't know. To me, it's kind of funny, this shape that is being generated here. Whoops. So this is the Epinechnikov, and and they all just have different different things. And let me just kind of show you. Here we'll do a sample of 30 points, and we'll plot just kind of some of these different kernels. So here's the Gaussian. If we so let me just show you a histogram of x. This is our histogram of x, and then for the Gaussian, and let me add a rug plot. So this is where the actual data points lie, and this is kind of when we throw a bunch of Gaussian curves on top of each other. This is the shape that we get. If I do rectangular, you know, it's a bunch of rectangles, and because all of these different plots, or all of these different data points, you know, the cutoffs are a lot more sharp. You get a lot of jaggies, okay, a lot of jagged things, okay. Same with triangular, okay, because the triangles, you know, get stacked on top of each other in a little bit way, and we can just kind of just see if I modify the bandwidth to be something smaller, they get kind of really you know, wild. Okay, in the same way that when you modify a histogram and you change the number of breaks, the appearance of the histogram can change quite a bit. You know, this is all the same data, just with different bin widths on the histogram. In the same way, when you change the bandwidth on your density plot, the resulting thing looks quite different. But it really, all of these things have the exact same underlying data. Okay. Yeah. Question.
How do you determine which bandwidth is the most representative?
Yeah, that's a hard question. Our defaults to having there's a formula for determining the bandwidth based on the number of observations and how much variation, the standard deviation of your observations. But it's kind of a tricky thing, and just like, you know, how do you decide how many breaks you should have in a histogram? There's not a solid answer that we just use for all purposes. We don't have an answer for what's the appropriate bandwidth for kernel density estimation. It's kind of like, let's just try this and see what it looks like, and does this look reasonable? It's kind of what we go along with. But you know, the default settings for R's density estimation is generally going to do a pretty good job. It uses a Gaussian kernel, and it has a formula for determining the bandwidth, and a lot of the times it gives what I feel to be, you know, reasonable as far as the way our data looks. Okay, and you can always include what we call a rug plot, which just shows little carpet hairs right at each data point location, and so you can kind of see for yourself how dense your observations are in the plot there. Okay, well anyway, that's kernel density estimation. I thought it was just kind of a fun little topic to go over, and because it is used quite a bit, and a lot of times, you know, sometimes you see graphs and you have no idea where these things are coming from, and it's basically just the computer adding these little wires that get stacked on top of each other. All right, well, that's it. It's been a pleasure, and good luck as you guys study, and we'll see you guys for the final exam. So.